Welcome to the Explainer. So if you're a focused learner looking to really master Python, you've absolutely got to understand the gears turning under the hood. Today, our mission is to completely shatter your current mental model of how Python manages data. We're going to unlearn some deeply ingrained habits and reconstruct a perfectly accurate picture of Python's memory management step by step. I want to kick things off by asking you a kind of provocative question. Are Python variables just labeled boxes? I mean, if you're coming to Python from languages like C++ or Java, you almost certainly think so. The traditional way we're taught programming is to imagine a physical box, right? You write a label on it called X, and you place a value like the number 5 inside that box. But here's the truth. In Python, that whole labeled box concept, it's a dangerous illusion. Believing it will literally inevitably lead to bugs in your code.
Okay, let's dive into this. Here's our roadmap for today. First, names not labeled boxes. Then, dynamic typing, mutability, scope rules, identity versus equality, and finally, memory management. We're taking a sequential journey from high-level coding philosophy straight down to low-level memory mechanics. Let's get started.
All right, section 1, names not labeled boxes. Before we write another single line of code, we really need to correct our core philosophy here. We have to completely change how we visualize our variables. In Python, variables are simply names. They're just labels that refer to objects residing somewhere out in memory. The core concept here is name binding. When you use the assignment operator, that equal sign, you are not stuffing a value into a container. Instead, you're binding a label to a specific, totally independent object. Just imagine an animated arrow moving directly from your variable name over to a memory address and pointing right at the object itself. The object exists entirely on its own in memory. Your variable name is really just a sticky note attached to a string, pointing the way to that object. Moving right along to section 2, dynamic typing and rebinding. So what happens when we start messing with our code on the fly? Well, the reality of dynamic typing is that because variables are basically just sticky notes pointing to objects, the variables themselves literally do not have fixed types. The type, whether that's an integer, a string, or a boolean, belongs entirely to the object in memory, not the name. Think about that animated arrow again. A single name can point to an integer right now, and then just shift over to point to a completely different object type, like a string, in the very next line of code. The label doesn't care at all what it points to.
And that dynamic behavior? That's what we call rebinding. Rebinding is just changing what a name points to using that equal sign. Visually, imagine grabbing that arrow, tearing it away from the old integer object, and establishing a brand new connection to a new string object. The old object hasn't been changed by this action at all. It's just been left behind. You haven't altered any actual data. You've simply moved your label to a new destination.
Okay, let's get into section 3, mutability and shared references. Now, this whole reference-based philosophy we just talked about is incredibly powerful, but it definitely introduces some dangerous pitfalls, specifically shared references. Because names are just pointers, you can easily have multiple variables pointing to the exact same object in memory simultaneously. If you have multiple variable names, their arrows can all converge on one single memory address. They aren't copies of the data, guys. They're basically different doors leading into the exact same room. So it's absolutely crucial to understand how different types of objects react when you have these shared references. Let's walk through this behavior. If an object is immutable, like an integer, a float, a string, or a tuple, its contents cannot be changed after it's created. If you try to modify an immutable object, Python actually just creates a brand new object at a new memory address and redirects your arrow there. But if the object is mutable, like a list, a dictionary, or a set, it can be modified in place. The object physically changes, and those changes are instantly visible to every single name that references it. This fundamental difference dictates exactly how your program's data flows and evolves. And that brings us directly to mutation. Mutation is when you change the internal state of a mutable object itself while your variable name stays bound to the exact same memory address. For example, if we append a new number to an existing list, the memory address doesn't change, the arrow doesn't move. Instead, the object itself simply expands right there in place. And guys, here is a massive bug alert. This catches almost every single Python beginner. Because assignment shares references instead of actually copying data, mutating a mutable object through one variable will unexpectedly change the value seen by all the other variables pointing to it. If 3 variables point to one list and you append an item using variable A, variables B and C instantly reflect that change too. This is the root cause of countless logic errors. To solve this, and to avoid those unintended side effects, you absolutely must explicitly create an independent copy of the object using methods like .copy. All right, section 4, scope and naming rules. Now that we know how these labels attach to objects, we've got to respect Python's strict naming constraints contextually within our code. Let's rapid fire through these. A variable name has to start with a letter or an underscore. It absolutely cannot start with a digit, and no spaces, hyphens, dots, or punctuation allowed. They're also super case sensitive. A capitalized customer underscore name and a lowercase customer underscore name are entirely different variables in Python's eyes. You also can't use reserved keywords like if or class. And hey, beware of built-in shadowing. If you name a variable after a built-in function like list or print, you basically make the original function inaccessible in that scope, which is going to trigger a type error. Finally, if you try to access a variable before you've actually bound it to an object, Python will throw a name error. Next up, section 5, identity versus equality. Since we're dealing so much with references and memory addresses now, how do we properly check our variables? Well, we have to explicitly contrast checking values versus checking memory locations. The double equals operator checks for equality. It basically asks, are the values held by these objects identical? But the is operator checks for identity. It asks a much deeper question. Do these two variables point to the exact same memory address? This distinction is totally critical. You could have two distinct lists with the exact same numbers inside them, meaning they're equal, but they reside at different memory addresses, meaning they do not share an identity. But you've really got to watch out for a behind-the-scenes secret we call the interning trap. You see, as a sneaky little implementation detail to save memory, the Python interpreter will actually sometimes reuse small integers and short strings. This means the is operator might return true for two variables you thought were completely distinct simply because Python decided to recycle the object when you weren't looking. Because of this unpredictable recycling, you should strictly use the is identity comparison only for singletons, meaning unique, one-of-a-kind objects like none, true, or false. And finally, section 6, memory and reference counting. Let's peel back the curtain on the underlying engine that automatically cleans up our memory. We're going to slow the pacing down for just a second here to deliberately walk through the life cycle of an object, from creation to deletion. Step 1, an object is created in memory, and Python gives it a reference count of exactly 1. Step 2, as you bind more variable names to that object, that reference count ticks up. When you reassign names away from it, the count ticks down. Step 3, eventually, if no names are pointing to that object anymore, the reference count hits 0. Step 4, the very moment it hits 0, Python's garbage collection system automatically kicks in and reclaims that memory space for you. Which brings us to a huge misconception about the del statement. So many people think del deletes an object. It literally doesn't. The del statement simply removes the name binding from the current scope. It just tears down the arrow. It does not delete the object itself if there are other active references still pointing to it. As long as that reference count is above 0, that object is staying right where it is in memory. So, bringing this whole thing together, now that you know variables are really just sticky labels pointing to independent objects, how are you going to write your next script to avoid shared reference bugs? By keeping this accurate mental model in your head, you'll be able to predict exactly how your data will behave, whether you're mutating a list or managing complex data structures. Thanks so much for joining me for this explainer, and I'll catch you in the next one.